Random variable, or for short RV here, is a big concept in statistics and probability. And so throughout this entire video lesson, feel free to pause at any time or even roll it back so that you can have a real clear and solid understanding before we advance any further step. To have a solid understanding of what a random variable is, how about let me start out with, and here I'm not even going to call it an example, it's just an explanation that starts with data 1 again. So let's look back at data 1. And like I said, like I made it clear right here, this is not an example, but we can just look back at some of the examples we have done and then build the idea of random variable from what we've learned. So data 1, when we were learning about the relative frequencies, then we already put data 1 into a table. And allow me here, I'm going to switch the format of the table a little bit before I reconstruct it. But so how about data 1 here? I'm going to put that in terms of 2 vertical columns here. And so and then here I'm going to call that the data values. And here we're only going to look at relative frequency. And so back in data 1, we already learned, after our study in the categorical data, and we built the relative frequencies of data 1, then, and of course, even though we, back in the, when we study about the categorical data, then we purposely treat data 1 as categorical data. But we can always put these things in the order like this. 60 is the first one in my value, and then we come 64, and then 68, and then we had 60 as being 3 out of 40, which was 7.5% relative frequency, and 64 was 4 out of 40, the n count was 40 for data 1, and then it was a 10% in data 1 being in the category 64, and okay, and so this is now my complete table of all listing in the different data values of data 1, and here I'm listing out the relative frequencies of my data 1 here. The only next requirement we're putting in here now is that for the long journey waiting ahead of us, each one of these percentage right here, each one of these percentages, why don't we put them actually into a decimal? So 7.5% is the same as a 0.075, and then this 10% is the same as a 0.1, and then this is a 0.125 in decimal, and 20% is the same as a 0.2, 15% is the same as a 0.15, this is another 0.15, and so on and so on. And so here we're looking at 0.125, and here we're looking at 0.025, and here it's 0.025, and here is 0.025. And so here it's just the next step that I'm putting beyond simply being a relative frequency, but I'll explain the reason why we had to do that. But once again, for any of those who already seen my video on how we can regard to data 1 as categorical data, then these simply came out from the actual count over the n count of data 1. So n count remained permanently 40 pieces of data, and so we came up with these percentages representing the relative frequencies. So now, we've been looking at data 1 for a long time and quite oftenly, but there has been one piece of information that we've never paid much attention to. But so if we look back into data 1 one more time here, and the unsorted, the unorganized version actually has a title. So data 1 here has a description, actually that's what I meant right there. But data 1 has a description that says any of these values represent a pulse rate of females So think about this data one we have here came out from a medical record right here. And so here I'm sort of halfway seeing data one as a categorical data. But on the other hand, let's bring back its own nature of being numerical data. So any of these readings right here, they came out from a measuring device right here. Think about this data came out from a medical facility. And so any of this value here, any of these values represent a pulse rate reading. And so generally we can regard to any of this. We can give and for us here at this, when we're learning stats, we're well familiar with naming a value, a numerical value, naming a quantity by a variable. So I'm gonna name any of my number here, any of the value here being a pulse rate. So I'm gonna name a variable to represent a pulse rate of female. And so once we name a variable just simply to represent a pulse rate of female, which I really hope that's not a surprising idea for anybody. It's just we have so many different values here, so we're just going to generally regard to any of these values as a variable we call x. And here the only thing maybe a little new for any of you here is that we're using a capital letter instead of the usual variable being in lowercase. So once we have named our variable capital X to represent the pulse rate, a pulse rate of female right here, then we've learned in probability that now we can start bringing up this question. In this data one right here, we can now, and it's all for convenience of use right here. Once we name the variable, then I can ask this question. P in parentheses. And once I finish writing it down, start making a connection with what we've learned earlier prior to this video here. But prior to this learning, then this means find the probability. Now how about the event I'm saying now is that x equals 72. So this statement now, after spending some time studying probability, then everybody is well understanding that this question is asking find a probability in the event that the variable we define here, or the x right now represents pulse rate of female. So find the probability in the event that a pulse rate equals 72. So 72 is the beating, is the value, is an actual value. So we want the variable x right here to equal 72. But simply take this as a probability question, then we already had an answer. The answer is among these right here. So when x equals 72, this is when x equals 72. It's right there. Then the probability correspondingly is right here. It's 8 out of 40 or 20% or informal decimal 0.2. So that answer there is a 0.2. We found an answer. We're reading that right out from the table. But that's, I hope at this point, once I brought up that question here, then you're going to start seeing my intention here. So what I just did here is I name any of these value with a general variable, and I let this variable to represent a pulse rate of female. And so now allow me to go back to this data, and how about I'm going to erase that name here. Instead of labeling this here any of these data values, how about I'm going to regard to them as the different values of our defined x variable. And so what we actually just realized now, we come to realize now, is that our relative frequency that we just saw that in our study, we saw that previously in our study of categorical data, but now in this concept of looking for probability, then these any of these values here is now can now be regarded as the probability that our variable equals any of the value here. And so any of the value here, I'm going to use a lowercase to indicate that. So here it's just a general description that when my variable equals any of the specific value on the left hand side column here, then any of these number here is the probability. And so to get comfortable with the idea here, so let X represent a pulse rate of female patient. If we want to find the probability that X equals 124 beats per minute. So our event is here. We want the variable lands on that value 124, and that's what capital X equals lowercase x is all about. So lowercase x is indicating a specific designated value on the list here, and capital is just capital X version is the general regard. And here we're looking at it's a probability statement. And so now this answer is right here. The probability when in this data one, of course, the probability of finding a female having a pulse rate being 124 beats per minute, that is a 0.025. And so that's now a new understanding. So on top of being a relative frequency, that in our study here, it becomes any of those relative frequency we've learned now becomes the probability that in our data, within our data, the chance to see a beating X, capital X equals 124 is going to be that chance of 0.025 here. And so we can also, what about those values that's not on the table? So if I'm asking find the probability where X equals 65, for example. So wait a minute, 65 is nowhere found in this table. That automatically means what? Think in terms of a probability. Then the chance that it happens in this data, 0 chance. So not being listed, there's still a probability. The probability where your variable equals this specific value, that probability there has to be equal to 0. And then we can also find other kind of probability question like that. Allow me to erase part of my work here, but I can bring up another quick question. What about from this data, find the probability when the variable we defined previously being value greater than 80. So greater than 80 means we're going to refer back to the table and only consider these values right here. So greater than 80 means we can be at 88, or we can be at 96, or 104, or 124. So anywhere in that zone right here, then we're going to sum up all the probabilities here. And so that equals to a 0.2 probability. It simply came out of 0.125 plus 0.025 plus 0.025 and plus the last 0.025. But that's how we ended up with that answer here. All right, so before we move on too far here, let's look back and find out what we did here. Or let's ask ourselves that question, what did we do? What we did here, data 1, we simply just arranged data 1 into a table like this. And similar to our discussion back in categorical data, then these are the different categories, but now still different values of your data 1. And then we realize that data 1, actually there has been that description of data 1 the whole time ever since our first look into it. And any of those data here means a pulse rate of a female patient. And so we have these different pulse rates right here beating among the female patients. And so we gave a variable name to represent generally any pulse rate of a female. And then at this point when I'm saying that we define a variable capital X, naming the variable capital X right here to represent our pulse rate, our quantity, our measurements in this data right here, then we're going to generally regard to any of these value as the X value, as the X data right here. And right at the moment, right at the instant that I was defining these readings right here, these pulse rate of female as a variable X right here, then I was highly confident that anyone viewing this video should be comfortable of defining a variable to represent a quantity, defining a variable to represent a value generally. And so the next thing here is that to the right hand side of this table, it's beside listing all the different values of the variable we are using here, of the variable x, then this right hand side is listing out the corresponding probability when in the event that the variable we named right here fall into each of these particular values. So in the event that x equals 60, we had a probability being 0.75. In the event that x equals 64, we had probability equals 0.1 within this data. And so that's what we did. We named a variable, and then each time our variable equals a value, an outcome, on the left-hand side column, and we treat it as an event, then we have a corresponding probability. So that's basically what we did. But now once we look through it, what we did, one more time right there, then we are ready to give a formal definition of what it means by being a random variable. So what is a random variable? A random variable, allow me to use it might seem a little funny, but I'm just trying to make it really solidly clear and crystal clear for anyone who are beginning into this understanding. But the number one requirement of being a random variable is it's just simply it's a variable. It's a variable as you already knew. It makes no difference with those kind of variable you already knew. And what I mean you already knew, meaning we don't have to wait until our time viewing this video to have that idea of using a letter to represent a quantity. And so a random variable, starting out, it has to be a variable as you already knew in its purest sense. But then if we look back into our demonstrating example that we were doing, besides being a variable, so here's the thing. You see, when we are studying algebra or even calculus or even any other class, any other math class besides the statistics, we've been so familiar with these kind of equations. Let's say y equals x squared, for example, or y equals 5x minus 1. This is a variable. That is a variable. And that is a variable. 5x minus 1 and equals y. So these are all variables. And then we had all those back in those times when we were studying these equations right here. We had all our times substituting in x equals 1 and x equals 5, and we substitute any values, and x equals negative 10. Negative 10, and we substitute any values into any of these equations, and we come out with the output value for y. So these are all values and values. But now think again at these equations. Put yourself back in that scenario when we were doing these equations and substituting values in these equations back in any of those other classes you took before the statistics here. Then think about it. There has never been any instructor in those other classes outside of statistics asking you, hey, in these equations, what is the chance, what's the probability that you're going to take x equals 5 and substitute that into this equation? No one asked about that kind of question. Even in calculus, even in differential equation, anywhere outside of statistics, nobody asked about what is the chance you're going to take x equals 5 and substitute into this equation. What's the chance you take x equals 5 and substitute in this equation? Because that's not the kind of application needed to be done there. Here in statistics, back in data 1, we did answer that question. We did answer what's the chance we took x equals, what's the chance we let x equal 72? And allow me to give the answer here without looking back at the table, because we already seen the table in our earlier part of the video. But probability when x equals 72 back in data 1 was 0.2 or a 20%. And that's what makes our variable here in statistics being different with the kind of variable that anywhere else outside of statistics is doing. Our random variable here, beside being a variable as we already knew it, the requirement number 2 here says each value assigned to the variable has an associated probability. So each value that we give to the variable, to our variable, there's a probability that we have to consider. So say when x equals 72, we assign 72 to the variable that we define, and variable here once again connecting with data 1 what we have seen in the demonstrating example. When x equals 72, or we're saying that we're assigning 72 to x right here, the chance in data 1, that probability is associatedly being 20%. And that's what it means by, so being a random variable. The first thing, it's a variable, as you already knew, and being the next requirement as important. Each value, each time we assign a value to the variable, there is an associated probability. The idea of, so why is it called random? Because that associated probability right here is referred to as the randomness. It kind of brings up the idea about, hey, there's randomness. How random? This is the randomness of the variable. And to be precise, of the variable's value, of each variable value. Yeah. So each time that we take each time the variable takes a different value, there's a randomness that comes along, and that's why this concept right here, this thing we're learning, is referred to as the random variable. Okay, so before we move on to any further discussion of random variable, let's look back at this table one more time, the table reorganizing our data 1 as a random variable. And so the left-hand side column here is listing out the different values of the random variable x, and the right-hand side here is listing out all of the different probability values corresponding to the different values of the random variable. But now the detail I would like to point out here is that if we add all of these probability entries, so starting from the first one being 0.075, and I'm adding to the next one below being 0.1, and I'm adding to the next one being 0.125, and I'm going to keep adding 0.15, and I'm adding with another 0.15, and add with 0.125, and add with 0.025, and I'm adding with another 0.25, and a last 0.025. So as I was going through that adding work, then somebody can already recognize that this should all be turn out to be 1. And so it's quite obvious, because apparently any of these probability value came out as a fraction out of 40. And so 3 out of 40, 4 out of 40 equivalent to 0.1, 3 out of 40 equivalents to 0.075. So all of these probability entries right here, it makes perfect sense that they are going to add up to be 1, or 40 out of 40. And so right now it's simply a detail needed to point out regarding this table. But later on, as we progress through our concept of random variable, this works right here, that we're adding up all the probability entries. The sum of all probability entries will actually become a requirement before we can take the random variable as a valid random variable to work with. All right, so now it's time to answer that question of why are we using random variable? What's good about defining a random variable? And what's all that benefits for doing that? And so we're looking back at our data 1. Weren't we just find earlier before this point that we were having our data 1 being put as a complete list showing all the repeats of 60s, all the repeat of 64, and etc. and etc. So we had a complete list, a complete full list of data 1. Why did we have to spend our time reorganizing the data 1 into Now first we define the random variable to represent a pose rate of female. Then we're going to start listing now all the distinctive values of the random variable x, which is our different distinctive data value in data 1, and then find the relative frequencies, and eventually and ultimately we call these the probability of each different value in our data. And we have to further ensure that all of these probabilities entries, as my work is still being written and shown up here, is we have to ensure that all the probability entries total up to 1. So why do we have to go through all that work right here? Is that just simply another the challenge we're putting up for ourselves? So all of that concerns about why we have to start using random variable, it's all because now we're going to start learning about the new concept. The whole reason of using random variable because we are starting to work with what's so-called population data. Okay, so what exactly is population data? And so a couple highlighted the understanding regarding population data. First of all, very big data or very large data. Think about our data 1 right here. It had only 40 pieces of data values, and these are representing pose rate of female. So ask yourself this question: is this data representing the entire population of female patients out there? I mean, we're talking about, if we're looking at the actual population of females, the world has not the world doesn't only have 40 females, and so the world of females is a lot bigger than this, and every female has a heartbeat, every female has a pulse rate beating, and so a data like this is, in other words, nowhere near to an actual population data. So just keep in mind that population data is the kind of data that's very large data. So how large? Nobody can answer how large, but it's so big to the point, very large data to the point that the n count, like say in our data 1 here, n equals 40, but in a population data, n count is we have to ignore it simply because it's just too big. So that's the number one characteristic of having a population data. It's just simply too big to the point that we just cannot look at how many data are being contained in our population data. We just know there's some kind of total data value, total number of data out there, but nobody even want to spend their time finding out what's that n count going to be. And so that's what I mean by the population data is the kind of data, very large data, to the point that n is ignored. And so to have a better understanding of population data, let me put back that data 1 here again. But this time I really need everybody who views this video to pretend. So now we're going to pretend that data 1 is a population. So we're going to pretend that data 1 is already a population of pulse rate. For female. And so consequently, it also means, why don't we all for now just forget about n is known to be 40. Let's just simply put it out of your mind. Forget about the n equals 40. Okay, because we're going to pretend that, hey, we got some data really big, And so why is it so important that I'm emphasizing forget about n equals 40. Let's pretend our data 1 is being a population data, being a population of pulse rates for female. The reason for that now is that because think about, hey, maybe we're so lucky that we have some kind of super powerful computer that stores all female pulse rate. Think about, medical facilities. They have computers with high storage capacity, big enough to store all of these data, to store all of their medical records. And so in that way, the computer knows to organize the data and put the data into these probabilities for us. But now when we are communicating with the machines right here, then the machine can only tell us that, hey, among the entire population of pulse rate right here, the chance of finding a female with pulse rate beating at 76 beats per minute is a chance being a 0.15 chance or a 0.15 probability. Or you can, for fancy purpose, we can think of that as 15% of time we're going to run into out of all that medical record representing, or out of the entire population, then the chance of having a female with a pulse rate beating at 76 is a 15% chance. But now I have to mention again, please do not assume that here we're looking at only 100 females and then there are 15 of them beating at this pulse rate. We don't know the n count. Remember I talked about we have to ignore, we have to forget n equals 40. And so think about, pretend that the whole reason that we know how we have these numbers simply because a super powerful computer gave us this data right here. And so we use the concept of random variable as a way to communicate about data that's being considered as population data. And so in that way, why was it, think about now, if if a data being handed to us, supposedly a population data. So if we're pretending now that this is a population data, we just simply don't know how big that is. In other words, we don't know how many 60s there are in this data. We don't know how many 64s there are in this data, because it's all we know is that 64 happens in our data, in our population, at the chance of 10% chance. The pulse rate beating at 60 beats per minute is happening in our population data at a probability of being 0.075 or a 7.5%. So in that way, now it becomes a crucial requirement that we must add up all of these probability entries. So 0.075 plus 0.1 plus 0.125. Remember earlier when I was adding up these probability entries where we were still seeing the actual data list, then this was just another detail to point out. But now think about when we're adding all these probability values up, why are they extremely important, crucially important? Because this is the only way to guarantee that no data count was missing. No data is being missing. So as long as this total of all probability entries sum up to 1 here, then it ensures that our probability has already been displayed in a complete display over here. That means all values are being displayed with their corresponding probabilities. Think about the worst scenario. I'm saying, what if the count that we're adding up here turns out to be what if that sum was sadly only 0.95, for example? Then that's going to be, the reason I really have to point out here, another reason here is a lot of time when data are being handed to us here in this way of setting, a lot of time it looks just so like a random variable, but it's dangerous. It might be dangerous that behind the scenes some value here are being undercount, some probabilities here are being undercount, and so it's extremely important that we gotta check for the sum here. When the sums fail to equals 1 right here, then if it's below 1, then some undercount happens, meaning either some other values that need to be displayed but the computer did not display for us. or maybe somebody was purposely hiding the data away from us. Okay, and what if the count here was 1.05 or something like that? And that means we got an overcount, maybe too much data. Something here, something among these probabilities were being overcounted. And so now, after we start having a better idea of what population data is all about and why it's important to use random variable here, then it's now time to give a good formal name to this table over here. And remind yourself, the characteristic of this table is it lists out values of your random variable. And in this quick little example of mine right here, the random variable x represents a female pulse rate, and then these are the different values that female pulse rate can equal to among our population of data, and then these are the probabilities. And so this table is referred to as the probability distribution. Of the random variable x. So x is the data. X is the data values, and this table right here is displaying all the probabilities. So a distribution is basically a list. It's showing the distribution of all probabilities, different probabilities on different values of our random variable. And so once again, coming back to that, sum of all probability entries, sum of probability, then anytime we're defining a random variable, then it will come to displaying the random variable as a probability distribution. Instead of being a list of 360s, 464s, like I said, the data is too big so that we can never really get all that count right there. How many times 60 happens in our data, how many times 64 happen in our data. We really have to give up with all that count. And we don't even know the actual end count, but instead we showed our data as a probability distribution instead of a complete list. And so that's why now it's, once again, it becomes more clear and more clear of why the sums, it's critically important why the sum of all probabilities must always equals 1. So it's becoming a critical requirement there. Before you can say a table like this to be a probability distribution. Okay, so we are now ready to work with our example 1 right here about random variable and how random variable plays an important part in working with population data. So I'm going to start out with saying, how about let x represents the age of a student at HD college. And so before I proceed any further and complete writing down my example over here, think about it a little bit. But the random variable x represents the age of a student going to college at HD college right here. But so now start thinking ahead already. There's not only one student going to school at the HD college. There's not only 100 students. There are generations of students going there, and each quarter, each year, there are tens of thousands. And so that's why this is a good place to start understanding that our data here must be a population data. Using a data size being only 40 data values or 100 data values will never be enough. We're looking at a real population data right here. A population data, a data that's so big to the point that we don't need to know any longer how big the data is. We have to ignore the end count here. And so think about the computer at the school here, the computer at HD college already, has been storing all of that records here. So maybe that computer, that super powerful computer, knows how big the data is, but when it's giving us the data, the computer only tells us that, hey, the chance that on this campus right here of HD college, the chance of finding someone who goes to school at 17 years old, is a chance of being 0.1. And the chance of finding a student going to school here at the age of 19 years old is a 0.25 chance, and the chance of having someone going to school here at age 21 is 0.45, and the chance of finding someone who goes to school here at age 23 is a 0.1 chance right here. And once again, we call any of these values on the right-hand side column of my current table the probability when your random variable capital X equals to any of these that we name them as a lowercase x right there. Okay, and so immediately after I complete writing down the table here, then it looks so like a probability distribution. Just like the one we've had with that we have built for our data one previously. But so now, before we can accept this table here as being a probability distribution, let's ask ourselves this question: is this table a valid probability distribution of the random variable x? Or if anybody claimed that, hey, let the x being the random variable representing that population data, is this a well-qualified probability distribution, meaning it has shown completely enough all the probabilities and all the value has been listed? And so the only way to check is .1 plus 0.25 plus 0.45 plus 0.1. And all these probability values here total up to be only a 0.9, which is not good for being a probability distribution. So as of for now, since we have an undercount right here, the answer to this is no, it's not a valid probability distribution. So what is the reason for that? So just think about, so first of all, I briefly explained, and let me explain again, but we already ignored the n count of how many students on this campus. Nobody know, and nobody really need to know. There are just simply some real big data that we call that it's a population data. So we already ignore the n count. So nobody knows the n count. All we know is that the chance of having somebody going to school, the chance that we find a student going to school here at the age of 17, that chance is being 0.1. But I also have to mention another critical understanding right here. It's even worse to understand this as there are only 100 students and 10 of them are being 17 years old. This is way incorrect, a way of a misunderstanding right here. We already ignore the n count, so do not assume any n count for your data. But so we already found that the total of all probability entries added up to be only a 0.9. And why did that make this table not a valid probability distribution of x? Simply because somebody is going to question us. If this is truly a probability distribution or being a valid probability distribution, then where's that other 0.1%, I mean 0.1 go? Where did that other 10% go? It's missing. 10% of data is missing. And so it could some of the entries here is being hidden, or some of the entry here is being undercounted right there. And so, and that's the reason why having a probability distribution where all of these probability entries add up and fail to be 1, this is where it fails to be a valid probability distribution. And in some other problems, it could be, who knows, we add up and we got a 1.05 probability total over here. And this is, sometimes we refer to that as an overcount right there. So some data must be way overcount. And So eventually I'm going to be using this particular data here for my later examples. So the truth here is that since this table fails being a valid probability entry, a probability distribution, then the actual corrected one is this entry right here was undercounted, and it supposedly a 0.2 there for that. And so now we are ready for working into our example 2 right here. So in this example 2, same data, but I made that correction that this entry right here, in the previous example, it was a 0.1, making it an invalid probability distribution. But here, correcting that to 0.2, now we have a valid probability. And you can simply check again that all of these entries on the probability side right here are added up to 1. And so now one last time I'm explaining about this table, but the reason we are using random variable, because it is impossible to go through and count all all students at HD college right here, and unless we leave it all for the computers, but nobody will want to individually count all of these values. And so the way computer is communicating to us here is that the chance of having someone going to school, the chance of seeing someone going to school, attending school at HD college being 17 years old is a 20% chance, or 0.2, and then etc. and etc. 19 years old here can be found at the chance of being 0.25 and all that. And so now, and we already checked that this is our probability distribution. So probability distribution of the variable x right here, because meaning it listing and it made a complete listing of all the values with probabilities being distributed. And so the question now, we can start asking, we can start answering a lot of questions here. That how about find a probability that we're gonna meet someone, or we're gonna find someone going to school here at the age of 17. And so that chance there now is a 0.2 chance, and we're reading it right out from our table. And then we can answer for ourselves other questions, such as, let's find the probability that on this campus we find someone who are going to school that is not 19 years old. And so here we can notice that x is not equal to 19 years old, means we're looking for someone who is going to school here, who is attending school here, but not, basically it's a negation of x equals 19 like that. It's another way of understanding that. And so in that way, we're just going to simply apply our rule of exclusion that we've seen throughout our probability discussion. And so here we're going to look for, purposely look for x equals 19, the probability when x equals 19, and we subtract that out from 1. And so all that here is going to give us a final probability being 0.75. And we can answer another question, such as find the probability that we're going to find someone going to school at HD college here who is being anywhere from 19 years old to 23 years old. And so now, so this inequality is indicating that when we're looking for those outcomes here, we want to include the chance of being 19. So the chance of being 19 is 25, but we also want to include the chance of being 21 here, finding someone being 21. So that chance there is 0.45 chance, and we also want to include the chance of finding someone who is 23, going to school there at 23 years old. So the chance there is 0.1. And so, and I keep saying including means we're going to be adding all of these probabilities here, and that sums up being 0.8 or 80%.